So we're continuing our discussion of subspaces, vector subspaces or linear subspaces. And I want to remind you the last theorem that we had. So maybe I won't write it as a theorem, but rather as a method. So in order to decide if a subset W of a vector space V is a subspace, which means that it itself is a vector space with respect to the operations that it inherits from V, we only need to check 3 of the, or 2.5 of all the axioms which define a vector space. Okay, and those are, namely, is a subspace. We need to verify, 1, that W is not empty. Okay, so this is not one of the axioms. This is one thing that we need to verify. So this is why I called it a half an axiom, 2.5. But usually the way we do this is usually check that 0 belongs to W. If 0 is there, then it's not empty, and then we get this one. And we need to check the 2 closure axioms. That if we take W1 plus W2, both of which are elements in W, that their sum belongs to W. And if we take a W in W and multiply it by alpha, then the scalar multiplication is closed. So these are little w's and this is big W. Maybe it's a bad choice of letters. Okay, so this is closure under addition. And this is closure under scalar multiplication. Okay, and once we know these 3 hold, then it's automatically a subspace. All the other axioms hold for free since they hold in the bigger ambient space V. Okay, so let's do a couple more examples. That's the title. And here's the first one. So example. So one thing that we're going to see is that there's a close relationship in several aspects between systems of equations and between, we already know that there's a relationship between systems of equations and matrices. Now we're going to see that there's in turn a relation to subspaces and spaces and methods coming from vectors and other concepts that we're going to learn about vectors and systems of equations. So all these things are intertwined. Okay, so here's one of these. So we can actually call this a theorem. In fact, it's even a theorem. So theorem. The solutions of a homogeneous system of linear equations is a subspace. So let's prove this. So remember that a system of linear equations we write of the form, so proof, remember that in general we write AX equals B. This is a system of linear equations, but we're looking at a homogeneous system. A homogeneous system means that instead of this general B here, we have the 0 vector as the vector of the constant vector, right? This is a homogeneous system. And so let this be a homogeneous system of linear equations. And we're looking for all the solutions, all the x's that satisfy it. They're vectors of length n, right? Where n is the number of variables, right? Or unknowns, okay? So what are the solutions? What do we need to verify? We need to verify that of all the vectors of length n, only those that solve this linear system are a subspace. How do we verify it? Well, we just said we need to check three things, right? So the first thing is, are there always solutions? Is the set of solutions non-empty? Okay?
No. Sometimes there is no solution.
That's wrong. There are always solutions to a homogeneous system because 0 is always a solution. Remember that? Okay, so let this be a homogeneous system and let W be the set of solutions. So W is a subspace of, let's say we're working over the real numbers, so it's a subspace of Rn, right? All the solutions are n tuples, okay, where n is the number of variables. And let's check the three properties. 0 is always a solution to a homogeneous system. Therefore, 0 belongs to W. And W is not empty, right? If we take two solutions, suppose x, let's call it x1 and x2 belong to W. So both of these are solutions, okay? That implies that x1 plus x2 belongs to W. And why is that true? We mentioned this. We said this property before. Because, since, what does it mean that these are solutions? It means that if I plug them here, I get 0, right? And what does it mean for this to be a solution, which is what I want to check, that if I plug this here, I get 0. And indeed, if I plug this into the system, I take the sum and check if it satisfies the system. Well, it does by the distributive property of matrix multiplication. This equals ax1 plus ax2. And since both of these are solutions, this is 0 and this is 0, right? So this equals 0 plus 0, which is just 0. So this solves the equation, right? Solves the system. And likewise, the third property, if we take x in W and alpha in R, some scalar, then alpha x is in W, since A times alpha x, this is what we want to check. Is this a solution? And indeed, the alpha can hop out. And since x was a solution, this is 0, so we get alpha times 0, which is 0. There's a little 0 here. I hope you can see it. Okay, good? Okay, so what we just did, which is not too difficult, is prove this theorem. Okay, because the three properties that we need to verify in order for the set of the solutions of a homogeneous system to be a subspace are satisfied. Okay, good? What about the solutions of a non-homogeneous system? Remark. Suppose we take a non-homogeneous system, ax equals b, where b is not 0. Are the solutions a subset? No, why not?
Could be empty. There will never be a 0.
Okay, first of all, it could be empty, right? That would say that it's not always a subspace, right? Because it could be empty. But what you said actually says that it's never a subspace because 0 is never there. 0 can never solve a system of the form ax equals b, where b is not 0, right? So the solutions of a non-homogeneous system, AX equals B, where B is not 0, are not a subspace, since 0 is not a solution. Never. If this is not 0, and you plug here 0, you get 0 on the left-hand side, right? So 0 can never solve a non-homogeneous system. Okay, good. One more example of... So these are examples that are a bit more, I don't know if to say challenging or intriguing, okay? They're more interesting than just taking a bunch of n-tuples and checking if they come from somewhere, from a more general discussion. And here's another one of that form, which is going to lead us to a whole new topic, okay? So here's another example of forming a subspace. So here's the idea. Remember that a subspace, okay, is we have this big set of solutions, a big sack here. Maybe you can look at me over here. Hello? Ah, there we are. So we have a big sack of vectors, right? In a big ambient space V, and we stick our hand in, pull out a few, and ask, is this a subspace, right? That's the idea. And in order for it to be a subspace, we can't just pull out any collection of random vectors. They have to satisfy the axioms, and what we saw that are the essential things that we need to check is that somehow 0 was there in the bunch that we picked out, and if we pick out any vector, all its multiples have to be there, right? And if we pick out any 2, their sum has to be there, right? So we can't just pick 3 vectors and ask, are they a subspace? They have to satisfy some things that force them to include many vectors, right? Okay, so here's an example. Suppose, for example, that we look at V. This is the ambient space, the big vector space, is going to be the set of 3 by 3 matrices over the real numbers. Remember this notation? 3 by 3 matrices. And suppose we want a subspace that contains a specific matrix. Contains, let's say, the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. This is clearly an element here, and we want a subspace that contains this matrix for some reason. Okay? What does it have to include? What does it have to include? Well, it has to include the 0 matrix, so we're forced to take that matrix as well. Just this alone would never be a subspace, right? So it has to include the 0 matrix. It has to include scalar multiples of this matrix. So all the matrices of the form alpha, 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 for any alpha in R, we called those, do you remember? Scalar matrices. Remember that terminology? All those have to be here. That's already an infinite collection, right? And if we add 2 of these, they also have to be there, but that doesn't add anything new, right? If we add a scalar matrix plus another scalar matrix, it's again going to be a scalar matrix, right? Alpha, alpha, alpha plus beta, beta, beta is going to be alpha plus beta, alpha plus beta, alpha plus beta along the diagonal, right? So the smallest, let's say, subspace that satisfies this meaning that it contains this matrix, is W, which is the collection of all matrices of the form alpha 0, 0, 0, alpha 0, and 0, 0, alpha, where alpha is in R. Do you agree? Okay? Because this, in particular, when alpha is 0, we get the 0 matrix, and this is closed under scalar multiplication and under addition. Does everybody see that? Okay? Suppose we want, now assume that we want also, suppose we want a subspace, that the smallest subspace is W. Good. Suppose we want also, let's say the matrix 0, 0, 1, 0, 1, 0, and 1, 0, 0 to be in our subspace. What do we need to take out of the SEC in order for this, including this matrix, to be a subspace? Well, obviously 0 is there because it was already here, right? Now we need all the multiples of this one, so all the matrices of the form beta, beta, beta across the inverse diagonal, the diagonal from upper right to lower left, right? But we need more. We need any sums of two matrices of these form to also be there, right? So we need a matrix that has, let's say, alpha, 0, and some beta, and then 0, alpha plus beta 0, and then beta 0 alpha to be there, right? So we need to take all the multiples of this and all sums of matrices of this form and of the form of multiples of this, right? Then let's call it the smallest such subspace. We can of course throw many other things in. We can take the entire V, and that's going to do it, but we want only the minimum necessary, okay? The smallest such subspace is, we can't call it W, let's call it U, which is the set, all the multiples of the first one we took, plus all the multiples, well, not plus, well, we can write it like this, plus beta times 0, 0, 1, 0, 1, 0, and 1, 0, 0. Any matrix of this form has to be there. And once all of these are in there, then the first one we wanted is there. All its multiples is there. The 0 matrix is there. The second one we wanted is there. All its multiples are there. And any sum of multiples of the two is also there, where alpha and beta are in R. Do you agree? Okay.
Are we allowed to do that, to assume we will always have the beta scalar in front of it, in front of the matrix?
No, what this means is the set of all matrices of the form some multiple of this one plus some other multiple of this one.
See,
I took a set. I'm allowed to take any set that I want.
But you basically changed the subspace, right? 'Cause it's not
This is not the same as this, of course. It has something that is not there, right? This is evidently a bigger set. It contains this set because if you take beta equals 0, you get all these matrices. So W is contained in U. U is a subspace. It's closed under addition, scalar multiplication, and it contains the 0 one. And it's the smallest one that we need to indeed contain both of these matrices. Okay? Clear? So this is going to lead to an idea that we're going to develop further in not in this clip, but in later ones. This is called, I'm just throwing the word at you, we're going to define it more carefully. This is called a linear combination. Okay? Some constant multiple of one plus some other constant multiple of another. This is called a linear combination. And what we did here is took all the linear combinations for any alpha and beta of the two generators, of the two matrices that we insisted on being in U. Okay, this is what we did. Okay, and this is a general idea that we're going to develop further. Okay? So whenever you have a big ambient space and you want to construct a subspace that contains any specific elements, this is what you need to do. Do you agree? Okay? Okay, so this is the end of this clip. I want to discuss even more examples of subspaces originating from taking, for example, intersections of subspaces. Do we get a subspace? If we take a union of subspaces, do we get a new subspace? That's the next clip.
Yes, last question.
Oh, question, yes.
The second matrix, if we were asked, this one, if it if W includes it, we would say no, right?
What do you mean if W?
If
This one is not an element in W.
we would definitely say that, right? Unless we change the subspace.
This matrix is not an element in W. W only has scalar matrices. Only matrices which have alpha, for some alpha, 3, 3, 3, root 3, root 3, root 3. This is not an element here. Good? Okay, now we're done.